All right, so here's our model still, and remember our null is that beta 3 equals 0, and beta 4 equals 0, and beta 5 equals 0. And our alternative is that one of these doesn't hold. So beta 3 doesn't equal 0, and or beta 4 doesn't equal 0, and or beta 5 doesn't equal 0. Okay, and so we're going to think of, again, the intuition here is that we're going to start to approach this test like, if we actually put these restrictions into a regression, we know that the sum of squared residuals is probably going to go up, right? The SSR is going to go up if we leave them out. So the kind of question we're asking here is that by including these variables, x3, x4, and x5 in our regression, are we decreasing the SSR enough to warrant putting them in? So that's the intuition behind what we're doing. Now in terms of the steps, we're going to come up with a restricted and an unrestricted regression. So here's our original model. We're going to think of this as being our unrestricted regression. It's our regression model before placing any restrictions on it, any of these exclusion restrictions. We're not putting any of these restrictions. So this original model up here in this case is going to be your unrestricted regression. Now we can think about, to come up with our restricted regression, or a restricted model, put null hypothesis, or enact your null hypothesis, or put your null hypothesis into effect in your unrestricted regression. So put null hypothesis into unrestricted regression, or enforce this night. Maybe I should say enforce null hypothesis in, or on, I guess would even be a better way of saying that, on unrestricted regression. So our unrestricted regression is kind of the original regression before we put any of these, before we're enacting any of these tests. But to come up with our restricted regression, which we're going to use to do this test, we're going to enforce this null hypothesis. So our null hypothesis is that beta 3 equals 0, beta 4 equals 0, and beta 5 equals 0. So let's call this regression 2, y equals beta 0 plus beta 1 x1 plus beta 2 x2. And now for this restricted regression, plus 0 times x3 plus 0 times x4 plus 0 times x5 plus u. And so these terms are going to drop out. And so our restricted regression would look like this. So you're just putting whatever these restrictions in your null hypothesis, you're just putting them into your regression and kind of reorganizing your regression. And so this is our restricted regression. All right, so we have this unrestricted regression, we have this restricted regression, and with these two models, we're going to come up with our test statistic, and it's going to be an F statistic. And so remember the intuition, I'll just put an equal sign there, is that does putting those variables in, putting these three x's in that we're testing, whether their effects are 0 or not, does putting these three variables into our regression decrease the SSR, the sum of squared residuals, enough to warrant actually putting them in there? So this is what our test statistic is going to look like. Sum of squared residuals from our restricted regression. So we'd run this regression here and get the SSR from that regression. we're going to subtract the SSR from the unrestricted regression. So UR or U. So from this original model, we would run this regression to get the SSR. We divide by Q, where this is the number of restrictions. So here, think of the number of restrictions. It's like the number of equal signs. 1, 2, 3. So Q equals 3 here, but we'll do an example. But Q equals 3 here. Or think of the difference in the number of parameters between this model. It's maybe even a better way of thinking about it. Think about, so here we have 1, 2, 3 parameters in this restricted model, and we have 1, 2, 3, 4, 5, 6 in this other one. So 6 minus 3 is 3. We get the same number. Okay, so that's the numerator of this test statistic. SSR unrestricted, so this same one here. And this is the denominator, n minus k minus 1. Again, n is the number of observations in our sample. K is the number of independent variables. And this extra minus 1 is for the intercept. So that's what's happening for that. And remember, our t ratio had a student's t distribution. Well, this f statistic is going to have an f distribution. And the f distribution has, instead of having just one degree of freedom that determines its shape, there's going to be 2 different degrees of freedom that determine its shape. And these degrees of freedom are important, right? Because they're going to kind of determine what our p-value and what our critical values are going to be. Because if they affect the shape of the distribution, they'll affect the area in the tail. We'll talk about it in a second. It'll just be a one-way test, but the area in the tail, in the right-hand tail of this test. And so the 2 degrees of freedom that determine the shape of this f distribution are q from this numerator, and then n minus k minus 1 from this denominator. So these two, now there's 2 degrees of freedom, and they determine the shape of this, the distribution of this test statistic. So let's kind of draw out kind of what we're doing theoretically with this f distribution. And again, we're going to come to a conclusion using either critical values or the p-value. But let's erase this and kind of talk about that. All right, so we're going to use the unrestricted and the restricted regression to come up with that f statistic like we just talked about, or we're going to ask Stata to calculate it for us. And then how Stata is coming up with, or how you're going to come up with a conclusion about a test is whether this f statistic is large enough to warrant rejecting the null hypothesis. So we'll reject our null hypothesis, so H0, H0 here, you don't need a comma there, if this f stat is large enough. So it's going to be a one-way test. And so here's different values of our f. Here's the probability density up here. And so our f distribution maybe looks something like this. Again, those 2 degrees of freedom, q and n minus k minus 1, determine the shape of this PDF here. So different degrees of freedom are going to cause different shapes. And so you're going to calculate your f stat. So let's say this is the actual f stat that you calculated or Stata calculated. And then, we're going to come to our conclusion by either comparing this f stat to the critical value where, 1 or 5 or 10% of the distribution is in this tail here, this right hand tail, or this tail over here. Or what we could do is we could come up with a p-value. So we could plot our f stat here and we could calculate all this area to the right. So this is the p-value. It's the probability under the null that we drew a test statistic as adverse to the nulls we did, given the null is true. All right, so that's how we're going to draw a conclusion about our f-stat. So one thing we should mention is if the total sum of squares, or sum of squared total, depending on which book we're using in terms of total sum of squares, the sum of squared total, we're using those kind of interchangeably, I guess, is the same in the restricted and unrestricted regression. What that means is the y variable is the same. Because it could be different depending on which restrictions we put in. So the y variable is the same. Then another way to represent this f-stat, and this is just algebra, is the r squared of the unrestricted regression minus the r squared of the restricted regression divided by q, 1 minus the r squared of the unrestricted regression, oops, I should say, yeah, unrestricted regression divided by n minus k minus 1. So this is just, again, and this has the same distribution, q, n minus k minus 1. This is just from, we kind of rearrange that other variable that we had, the other formula we had, using the fact that r squared equals 1 minus SSR over SST or TSS, whichever one. So that's just using this and some algebra, and you can change the other formula to this one. So this is how you see this formula sometimes for the F statistic. It's the exact same thing, you'll get the same numbers, but you can only use this formula if your y variable is the same. So if your dependent variable is the same in both regressions. And sometimes it's not, because if you're testing like a hypothesis, like let's say you're testing beta 1 equals 1 and beta 2 equals 0 or something like that, then our dependent variable will be different in the regressions because we'll have to move x1 over to the other side to test this. Okay, so we kind of know how this F statistic works. We're going to go through an example, and we can talk about a kind of a special case here where we're going to test whether all of our slope parameters equal 0, and that's called a test of overall significance. Let's do a quick example going through the steps with this. And then we'll talk about that overall regression, overall test